All right, so this is the presentation for Chapter 22 on nuclear chemistry. This is a bit of an aside chapter, not too much relevant to the main portions of this course, but we'll see some concepts in here that we will be bringing over, especially first order decay, that will go into the next chapters following to some more substantive things. This is the second part of the material for Test 1, along with the review material that was in the presentation before this one. So key points for this chapter for Test 1. Trends in nuclear stability, nuclear decay processes. Make sure you know all of these different processes. We'll go through them, but I just want to give you an assemblage here, kind of what are the main topics. You'll also want to check your study guide at the end of the module to go over the particular content with a little more specificity with what we'll be covering in Test 1. Also, nuclear fission and fusion, nuclear transmutation, dating with radioisotopes. So these are our main topics we're going to cover in this and the following presentation. Also, bonus on naturally occurring nuclear reactors. That'll be bonus number 2. That'll go along with you'll see that also in your study guide. There'll be a quick question about that. So we'll cover that close to the end of this lecture in the second part. So, like I said, radioactive decay is a first order process, and that's going to be one of the most important takeaway from this chapter, as we'll see in later chapters, especially into chapters 11 and 12. So remember that a first order process is one whose rate depends on concentration of the substance to the first power. So the rate is going to depend on how much substance there is. Again, we'll see this as we move forward into this chapter, but just keep this in mind because it's going to translate into the later chapters. Areas not to focus on. So this chapter has some kind of edification material that we're not going to cover in these lectures. Make sure that you know energy released in nuclear processes for the homework, but I'm not going to test this on Test 1. Although there's talk about nuclear reactors and some vocabulary and how they're structured. Again, not something I'm going to test, not something you're going to really see, but maybe look over it for a little edification, a little more practical application. Also, detecting and measuring radioactivity, the Geiger counters and Becquerel units and all that stuff. We're not going to cover that in Test 1, and it's not going to be a major point. Just keep in mind, don't focus on any of these in particular for the exam. Also, medical uses of radioactivity, detection of tumor markers and some of that other information. That's a little bit beyond what our focus on is in this course. So, key terms. So we're going to be using the periodic table to check back at various radioactive elements. So we want to make sure we're aware of the transuranium elements. This is a topic, right? Elements past uranium on the periodic table, all these are radioactive and artificially produced. Nuclear transmutation, the process of changing one element into another via nuclear processes. Mass defect, so this is the mass that's lost or gained when the nucleons fuse together or are broken apart. Binding energy, and that's that energy that corresponds to the defect. Again, we'll see the equations that go along with this later. We'll get to use E equals mc squared. It's kind of fun. But we'll come back to this later, but I want to make sure that these bold terms you're going to need to know in order to interpret problems both on the homework and on the first test. Also, nuclear fission, just have a general idea. That's the splitting of heavy nuclei. Chain reaction that goes along with nuclear fission, where bombarding neutrons sustain the process. Critical mass, if you have a sufficient amount to sustain those visible neutrons. Again, we'll cover it in a little more detail in a later part, but just keep these concepts in mind as we go through the material. And then nuclear fusion, where we're going to join things together, join nuclei together, join the nucleons together. We'll see a little more detail about that. So the text starts out by discussing these transuranium elements to give us a concept, right? All of these are radioactive. Now, there are other elements like technetium and some of the other elements even before uranium that only have radioactive isotopes, but all the ones past uranium are artificially produced and are radioactive. So that gives us a sense here. They mention technetium and promethium as specific examples that don't occur naturally. Sometimes you'll see on certain periodic tables they'll put those in a transparent because they don't have a naturally occurring isotope. Again, this is more what are they talking about, making sure we have a good concept of the scope as we move through the material. So if we're looking at the nucleus, which is a major focus of this chapter and this topic as opposed to typically chemical properties of elements, right? We're thinking about the nucleus itself. So there's a ratio of neutron to protons that sustain a stable isotope. And generally for lighter isotopes, lighter nuclei, we want to have about a 1-to-1 ratio, but as things increase, as the number of protons increases, it moves toward a 2-to-1 where the stability zone is. We can see that in this in here particularly, how when we're at a lighter number of protons or a smaller number of protons, there's a 1-to-1 relationship, and then as we move out, it moves toward 2-to-1, this kind of band of stability where the stable nuclei are. When we say something is stable, that just means it doesn't have a decay process that will transform it into something else. Some things are very long-lived, so they're essentially stable, but we've predicted or we've detected a decay process to occur in these isotopes, and some are mathematically predicted to be stable, depending on their properties. They talk a little bit about this little island of stability where people have also been able to produce some elements that have some stability up in here. But again, generally, for the purposes of chemistry, we're not really concerned about things too much beyond, 100 when we're doing typical chemical processes. But this gives us an idea of like why are they stable, and how can we make a little bit of prediction about whether a nuclei will be stable. So again, this breaks it down, zooms in on the previous chart in a little more detail to say, well, what happens, right? How do things get into that zone of stability? Because ultimately, the decay process is just like a chemical process. Things are driven by a tendency toward finding a stable position, a place of lowest energy, some kind of minimum, right? So the same thing is true of the nucleus. So as they say here, they've got a lower neutron to proton ratio, so they've got too many protons. They're going to try to release that positive charge in some way to get themselves to a more stable position. If they have too many neutrons, they're going to try to emit negative charge so they can get more positive charge. And the way they emit this negative charge is they call this a beta emission. It's really it's an electron that's emitted from the nucleus. And so this process will help to bring the nucleus closer to this zone of stability here in the middle. And that's sort of the goal of the system, is to try to get it to a more stable spot. So when a decay process happens, it's trying to move toward a stable isotope, or at least something more stable than where it was. And again, it's very similar to chemical processes, a tendency of things to move toward a more stable position. So every element on the periodic table has at least one radioactive isotope. That's nice to know. Some elements have multiple stable isotopes too. Some of the text doesn't really talk about. Hydrogen, they say, is the only element whose most abundant stable isotope has more protons than neutrons. It's a fun fact. It also has the deuterium isotope that's stable and the tritium isotope that's radioactive. The ratio of neutrons to protons gradually increases. Like I said, it moves toward from a 1-to-1 to a 2-to-1. Not terminology used in the text, but another way to interpret what they're saying. And all elements heavier than lead. Now, the text said that heavier than bismuth, but that's technically not true. Bismuth doesn't have any truly stable isotopes, but it's so stable that it's like longer than the age of the universe, in its most stable isotope in terms of its decay process. We've never actually observed it decaying, but we predicted it to decay. So while it's safe to handle and it doesn't decay very rapidly, it's a very, very, very long half-life, it technically does not have a stable isotope. So I adjusted what the text said here to update it with a little more current information. So nuclear processes. So these are the processes that we looked at when we were looking back at the earlier part of the slides, kind of the key terms. So what they call an alpha emission is an emission of a helium atom from the nucleus, right? It loses 2 protons and 2 neutrons, so it loses a mass of 4 and it loses a charge of 2 when this is just emitted. They called it an alpha particle because at the time when people were evaluating radioactive decay, they didn't know about all the different positions of things necessarily on a periodic table or what these charged particles corresponded to. They just knew what the charge was, and they called the first one they detected alpha, and the second one beta, and the third one gamma, just like ABC in Greek. So the alpha emission today we know is as we said here, and the beta emission turns out is an electron, but this emission process was discovered before the electron, so they didn't have a name for it quite yet. So you'll see both of those terms, both the beta and the electron symbol being used. They'll use the E and they put a -1 there to indicate the charge. If they don't put a -1, it's assumed to be positive, so it's a positron, as they show in the positron emission. Although sometimes in notation, just keep aware, they will put a plus sign there, especially just to make that distinction a little bit clearer. Gamma emission is a high energy photon. It's just light being emitted, so it has no charge, and it's always written with the little gamma symbol. An electron capture is where the electron is actually pulled in from the surrounding cloud of electrons in the atom. So that will end up reducing the atomic number. It has essentially no effect on the mass because electrons only have about 1 over 1800 the mass of a proton or neutron, about 1/2000 the mass. So it doesn't change the mass number effectively for the nucleus. There's a little change, but it's typically not noted in the way that they break this down. So keep in mind the way they wrote this also here in the symbols. This 4 here is the mass number, that they write mass at the top, which is the sum of protons and neutrons, and then they write protons underneath. This is notation that you would have learned in like a 151 class. I'm just trying to make sure we have a little refresher, that mass is written on top and then charge is written below, and if there's not a negative sign, it's assumed to be positive. All right, so they break down the processes again here with sort of a more written notation that's out of the table. A neutron turns into a proton plus this beta particle that's an electron in beta emission. So essentially an electron appears spontaneously out of the nucleus, and then that allows for this nuclear transmutation to happen. Positron emission, a positron, which is the antiparticle to an electron. It's positively charged, but it has the same mass and all the same properties, except that it's positively charged. So it just appears outside the nucleus, and that allows for a change from a proton to a neutron by conserving charge, right? These nuclear processes, much like chemical processes, have to conserve charge, they have to conserve mass, they have to conserve all the same things that we've already learned must be conserved in chemical processes. And again, in an electron capture, an electron and a proton come together. Essentially, the electron falls into the nucleus and merges with it and turns that proton into a neutron. And then in alpha emission, we see that we have the loss of this alpha particle, and then we have the production of some new nucleus, -4 of its mass and -2 of its charge. And typically this notation A and Z is used, where Z is the charge and A is the mass. Sometimes they'll use other symbols for this in A, but Z is pretty standard as the charge specifically. So if you see that in any homework questions, keep that in mind. So they say here, which of these two isotopes, one of them decays by beta emission and one by alpha emission, and so which is which? So how would we tell? So they're both isotopes of gold, that's what Au is, and one of them has a lower mass and one of them has a higher mass. So if we go back to our so if one of them has a higher mass, that would mean that it has more neutrons, because if we change the protons, then it wouldn't be gold anymore. So something with a higher number of neutrons has a higher neutron to proton ratio, so that will be the one that's more likely to undergo beta emission. Okay. The same principle will also apply for the second question, because they say here one decays by positron emission. So if something's going to undergo a positron emission, again, that will be the one with the lower neutron to proton ratio as seen in here. Okay. So that will give you a way to approach problems like this that may come up in particularly in a homework question. I don't ask questions like these, but I wanted to just make sure we address an application of using the chart that we just went over, how we can identify what kind of process would happen just by looking at the mass and the element's identity and be able to make a loose prediction. It's not about predicting something absolutely. It's about getting a sense of what is most likely in terms of the trends that we know. Okay, so energy changes during nuclear reactions. So they say here that in principle it's possible to measure the strength of forces holding a nucleus together. Okay, and when a nucleus breaks down or a nuclear process happens, there's some kind of energy exchange that's going to be associated with that process. So they give us an example here of a helium-4 nucleus where it's formed by the addition of 2 hydrogen nuclei and 2 neutrons are going to come together to make that. And there's going to be some kind of change in energy with it, just like there would be with a chemical process, right? And it can be either it can release energy or it can require energy depending on the stability of the process, just like a chemical reaction that's endothermic or exothermic. And again, a good vocab point here that they use sometimes the term nucleon to refer to the proton or the neutron. I've used that already in the presentation, but it's a good point that we've got a little definition here. So many nuclear processes have a very, very high activation energy. It's the same kind of concept that we'd see in a chemical reaction where we have to supply some kind of activation energy to be able to start a chemical process. The issue with most nuclear processes is that the activation energy is just enormous, like energy from the interior of the star. I mean, we're talking ridiculous amounts of energy, many orders of magnitude higher, 5, 6 orders of magnitude higher energies of these processes as compared to typical chemical processes. So this is where we bring in the E equals mc squared that we mentioned before. We can use this if we can calculate a change in mass that occurs during the nuclear process, which is typically how we can classify what happens. Some mass is changed into energy in these processes directly. So if we can find that change, which they call the mass defect, that's earlier vocab, that delta M, we can calculate what energy that would correspond to. And if that change in mass is positive or negative, that will also change the sign of the energy, so we can also figure out the direction of the process. Does this particular nucleus gain mass when its nucleons are fused together, or does it lose mass when its nucleons are fused together? If it's losing mass, then there's going to have to be some corresponding release of energy. Mass was converted into energy. If it gains mass, then that means energy had to come in from the outside, just like an endothermic process would work. So, and another reminder about the atomic mass units, right? This is kind of a connection to the stoichiometry concepts that we saw in earlier 151 chapters. Just so you know, when they made those measurements, they took 1/12 the mass of a carbon-12 atom, and that mass is a mass that is the actual mass of that isotope and the mass that would have been fused together. So it accounted for the fusion energy, it accounted for that mass defect that we're talking about when we measured the mass of that isotope. It wasn't just like 6 protons and 6 neutrons. It was the mass of a carbon-12 atom. And when carbon fuses, it actually releases energy. So the mass of it is actually a little bit less than the mass of 12, even though we say it has an atomic mass of 12. It's a little bit off for that reason, because there's a little bit of defect going on in there. That's where the energy change actually occurs. So again, just a reminder, we've mentioned the mass defect here. So in typical chemical processes, we have to conserve mass, right? But in these nuclear processes, we do convert mass into energy with E equals mc squared. So we've got a more universal law of energy conservation that's going to be at play here. So just sort of keeping that in mind. We mentioned the mass defect. Again, that's going to be the delta M in the Einstein equation that we're going to use, and the binding energy, which is the energy that's associated with that mass defect. So we see that at iron 56, that's where our binding energy reaches a maximum. So as things go down, we're going to start, instead of, so as heavier things fall apart, they actually release energy. But as lighter things fuse, they release energy. That's kind of the concept that they're showing here in this chart. So as a result, they say nuclear stability increases when lighter elements fuse together and when heavier elements split apart, as shown by the arrows. So it's at iron where those two factors equal out, where it's approximately, there isn't really any mass defect going on. Now around there's no real difference between whether they're fused or not in terms of the stability of the process. But as we start to fuse heavier elements than iron, now it's going to start to cost us energy. So these elements are typically only forged when a star is dying or when a supernova happens. But any processes earlier than that can, in theory, sustain a star because they're releasing energy. So key points to keep in mind. So we've got a quick worked out example. Now, I don't have problems like this on our test, but I want to show you this because there will be some homework questions that involve using this as a kind of quick example. And just as a note, after this problem, there are some other additional examples in the text. And if you want to do those answers, they're of course in the back chapter. It's got a key along with it. So they mention here that helium-6 is a radioactive isotope, and they give a half-life. Okay. And remember, this is a first-order process. Nuclear decay is a first-order process, so a half-life pertains to that. We'll talk a little more about that in the next presentation. But so calculate the mass defect of the formation of the helium-6 nucleus, okay, and they calculate the binding energy. And they say, is it more or less stable? And they ask a number of different questions. So first, they calculate the total mass of the nucleons if they were free, and then they calculate the mass of the helium-6 nucleus. Now, when you do this, you're going to want to make sure you use a periodic table that gives you these masses out to a fairly significant number of digits. I mean, a lot of times students, when they're calculating mass, they'll only use maybe 2 or 3 digits after a decimal point. As you can see here, they're using 5 digits after decimal point. You may want to look up 8 in order to find these actual differences, because sometimes the difference in mass change can be very small in order to calculate these defects. A problem should give them to you in the homework, but if you don't, because they gave it to us here at the top, you can see they gave us the 1 mass here. But you may need to look up these additional information or make a note of the mass of the neutron and proton that are given here for the problems that you'll need as you go forward. So we calculate the mass of the protons and neutrons individually, not fused together, and then we calculate them as fused together. And we can see that those are, there's a greater mass to start with when they're individual than when they're fused together, and that will be the defect. When we subtract the, here we go, when we subtract the mass of the nucleons, subtract the mass of the nucleus from that, we'll get the mass defect. Now, of course, this is in atomic mass units, so we'll have to convert that into grams using a conversion factor. There's also a common conversion to kilograms as well. For our sake, they're doing it just to grams here as this step to get a grams per mole calculation as a defect, but because that's what the problem was looking for. But if you just calculated it as grams and you were looking at it for just one atom, you'd be able to use what they immediately calculate from the conversion to grams. Then we'll pull in the Einstein equation to convert the mass defect into a binding energy. And there we'll need to convert that to kilograms. That's something to very much keep in mind. Because of the way the Einstein equation works and puts things in joules, we'll typically want to have our masses in kilograms. So if you don't need to calculate the defect in grams or grams per mole for a problem, they just want you to calculate directly to the energy, you can just skip converting it to grams and use the proper conversion factor straight to kilograms. Keep that in mind. And we can use the 3.00 by 10 to the 8 for the speed of light. We don't typically need a lot of precision there. Our major point in making sure we get correct answers out of this is making sure we get a good mass for the nucleons and a good mass for the nucleus, and that would mean using the numbers the problem gives you, or going back to this as an example to get your references for the masses of protons and neutrons. So here we're able to calculate it, and we can see it's a pretty small number here in joules, 10 to the minus 12, but we're just talking about one atom here. We're just making one unit of this, okay? So as we convert this into binding energy per nucleon, which is typically how they reference it, how they put it on the chart that we saw, what really I think is more striking is the binding energy in kilojoules per mole. So that would mean if you could fuse a mole of these, how much energy would you release in kilojoules? So now you're able to finally see the large numbers, the 10 to the 9 numbers of kilojoules that correspond to the large scale energies of nuclear processes that we mentioned earlier. That's really the key there. A lot of times, like I say, problems will focus on these binding energy per nucleon. They'll often want you to stop there. So you'll want to just make sure you count up all the nucleons. Like here we have 6 in this helium-6. That's where they're getting at the nucleons, or just the mass number. But what really is more striking to me in these problems is the final answer here, the binding energy in kilojoules per mole, because that's what gives you that comparison to chemical reactions, as we've been saying. But come back to this example. If you see questions like this, if you're working through them in the homework, this example is worked on the text is a really great one. And like I said, there are also some other ones that you may want to check if you're working on them yourself, and the answers will be provided with the answer materials. So I'm looking at this example only because I want to, again, show you the comparison to chemical reactions. So they say, if we typically think of a mass change as happening in a nuclear process, right, that's where we're getting all of our energy, do we also have mass changes in chemical reactions? Well, we do, but it's at a much smaller scale, because chemical processes don't cause a lot of mass change. Now, when you think about it, E equals mc squared tells us that when we bind energy into a process, like if we have a molecule that's at a higher energy state than another, or a different way of configuring atoms that's a higher energy state than another, that there should be some change in mass that corresponds with that change in energy. And that is true. It's just that for most chemical processes, that change is so small that we can't measure it by comparison to the typical thermodynamic parameters and changes of energy that we derive that way. Like the scaling is just so different, right? So they say to calculate a mass defect when some energy change of a reaction is known. So they say we're going to bring together 2 hydrogen atoms, and we've got some delta E that corresponds to that process, because this is just a purely chemical process. We're not doing any kind of nuclear process here. And they say, what if we worked out the Einstein equation for that and calculated what change in mass would go along with this? Here they have it as grams per mole. A change in the molar mass is the way that they've got it framed here. Having 2 separate hydrogens and then putting them together. That sounds kind of silly because they're typically just additive in a chemical standpoint, but bringing them together does have a corresponding molar mass change. It's just 10 to the minus 9. It's just ridiculously small. So the mass changes associated with chemical energies in chemical processes are so small that just not really significant to even measure. But the point is that the equation does still have applicability there. And it also shows us how grander the scale is when we're doing these nuclear processes compared to chemical ones in terms of the energies absorbed and released. So that's a good aside just to think about that and keep the scale in mind here. They say that much too small than the amount to be detected by any balance. So no balance exists that you could be measuring masses like that. You'd have to use a process that's far beyond any typical chemical balance. And far smaller than the mass defect of a stable nucleus, which we calculated to be 10 to the minus 2. So if we were fusing them together, we would be seeing a much larger change in molar mass from that if we were fusing them from nucleons. Okay, so we're going to take a quick look here at the fission and fusion processes, right? So this is if we're going to break apart a very heavy nucleus or we're going to put together lighter nuclei together. And it gives us a little bit of history here since the discovery of this in the 1930s and 40s. And again, we're going to be coming back to that, I think, though, a little bit later. So this will be the end of this presentation, and we'll come back to that topic in the next one. Thanks so much.